We're going to start today by talking about the fundamental theorem of calculus and tie that in with the concept of definite integrals. Fundamental theorem of calculus says let f of x be an antiderivative for little f of x. So big F of x is the antiderivative. Then what we do is introduce the concept of a definite integral. We've seen indefinite integrals before, and definite integrals just differ in the fact that we have an upper bound and a lower bound on the integral sign. Well, the lower bound is your a, the upper bound is your b. So the definite integral from a to b of little f of x dx is just equal to big F evaluated at b minus big F evaluated at a. In other words, all I do is do the same process I did before. I find the antiderivative, and the difference here is I take the antiderivative and evaluate it at b, and then take the antiderivative and evaluate it at a, and I subtract the two. Let's see how this works in an example. This is an indefinite integral, the integral of x to the 7th plus 5 dx. We know when we integrate this, this is going to give us 1/8 x to the 8th. We add 1 to our exponent, then multiply by 1 over that number, plus 5x plus c. Remember, an indefinite integral gives us the class of all antiderivatives. So this is, every antiderivative is going to look like this. We know antiderivatives are not unique because we don't know what the constant is, because when we take the derivative of every constant is 0. However, your fundamental theorem of calculus says we just want an antiderivative. We don't have to have a specific one. So what we're going to do is when we do the definite integrals, we're going to get rid of the c and just assume c is 0, because that is definitely an antiderivative. Now let's look at a similar problem. We're going to have the same function, but we're going to use a definite integral. We're going to go from 0 to 2 of x to the 7th plus 5 dx. Well, if you notice now, this is set up like our fundamental theorem of calculus, this left-hand side. The difference here is our right-hand side, we don't want to just take an indefinite integral. We want to take this indefinite integral and evaluate it first at b, and then evaluate it at a. To do this, what we're going to do is in 2 steps, we're actually going to take the indefinite integral. We're going to actually calculate, use this part. So I'm going to sit there and say the integral from 0 to 2 of x to the 7th plus 5 is equal to 1/8 x to the 8th plus 5x. Then I'm going to use this notation at the end. This should be probably extended a little bit longer. All this says is I'm going to take this function and evaluate it from 0 to 2. So what it means is I'm going to do what the fundamental theorem of calculus says to do, which is to first plug in 2. So I'm going to take this function, plug in 2 into this 1/8 x to the 8th, so it's 1/8 to the 8th plus 5 times 2. 1/8 to the 8th is just 32. 5 times 2 is 10. And then I'm going to subtract it from the same function evaluated at 0. Notice these 2 sets of parentheses here and here are pretty much the same thing. All I'm doing is plugging in the upper bound in the first one, the lower bound in the second one, and then I'm going to evaluate 32 plus 10 minus 0 is simply 42. Let's look at another example. Again, we're going to apply our fundamental theorem of calculus. We pretty much know to do this every time we see definite integrals. I have x to the square root of x times the square root of x, 8 times the square root of x plus 6x. Remember that the square root of x is just x to the 1/2 power. So when you integrate this, you're going to get 16/3 x to the 3/2 plus 3x squared. Again, to check this, we can just take the derivative of this and we should get this function inside. And again, we're going to evaluate for this from 9 to 1. So I'm going to take this entire function, evaluate it at 9, and then again I'm going to take the entire function, evaluate it at 1. Now, fractional exponents are sometimes difficult, but we take the square root of 9 and we get 3. 3 cubed is 27. 27 divided by 3 is 9, and 9 times 16 is 144. This is 9 squared is 81 times 3 is 243. And the nice thing about plugging in 1, the only thing easier than plugging in 1 is plugging in 0, but plugging in 1 just gives us the coefficient. So 16/3 plus 3. And if you do your work here and get a common denominator, find the answer is 1136 over 3. Let's do one last example. Integral from 3 to 6 of 1 over x dx. This is, again, isn't that difficult. We just need to remember that the integral of 1 over x is natural log of x. So I'm going to evaluate the natural log of x from 3 to 6. So I take natural log of 6 minus natural log of 3. And now we need to simply use our log properties. We know the log of 6 minus the log of 3 is equal to the log of 6 over 3, because when I subtract logs, I can bring them into a single log and divide, which is the natural log of 2. Now, for the rest of this chapter, we're going to look at it applying the fundamental theorem of calculus to different applications. Let's look at our first one. What do definite integrals give us? When I have a definite integral from a to b of f of x dx, a definite integral of a function gives us the area under the curve of f of x. In other words, the area between f of x and the x-axis from the point A to the point B. So in other words, if I have this function here, in this case it's just a straight line, from the point A, remember A and B are x values, so from the point 5 to the point 9, if I take the integral of this function, this definite integral, this will give me the area, the shaded region under the curve. So if I write this down, this will be the integral from 5 to 9. Again, we're going to be using x values because I'm integrating with respect to x. And this is the function. If we actually calculated this, which we've done earlier in this course, this is simply the function x plus 5. Let's see if we can do an example with this. Calculate the definite integral from a to b of f of x dx, f of b minus f of a. This is our fundamental theorem of calculus. Basically what this is going to do is give us the area under the curve of this function. So again, just like what we've been doing, this is 1/2 x squared plus 1/2 x from 0 to 1. And again, we're going to evaluate at 1, we're going to evaluate at 0. And that gives us 1/2 plus 1/2, which is 1, which tells us the area under the curve from 0 to 1 of this function is equal to 1 square unit. Here's another one. Find the area under the curve over the indicated intervals. I have y equals 2x. I want to go from 2 to 4. Well, notice this is the lower of the two numbers, so this is your lower bound, this is your upper bound. This is simply your function. So I'm going to integrate from 2 to 4. Of my f of x is just 2x dx. So when I integrate 2x, I'm going to get x squared. And again, I want to evaluate this from 2 to 4. And again, it's just plugging in 4 and then plugging in 2 and subtracting the 2. 4 squared is clearly 16, minus 2 squared is 4. So we have 12 square units is the area under this curve from 2 to 4.